So today we are going to start looking at the other side of exponential relationships. It's almost like you have deja vu. Up until now, we have only had exponential growth. In other words, we have had money, rabbits, ballots. All of these things have been growing at an exponential rate. But it is also possible for things to decay exponentially. And for those of you who are going into or hope to go into medicine, this becomes a really important idea because your body will break down the medicine that you take at an exponential rate. For those of you who are looking into nuclear physics, which would be really cool, radiation will break down exponentially. For those of you who want to follow in the footsteps of Mrs. Yema and go sit out in bleak deserts, chipping away at sand and rock, looking for dinosaur bones, you'll be using exponential decay to figure out how old the bones are that you discover. So exponential decay is all around us. It's something that we need to be able to understand and model mathematically because it helps us understand the world around us. Make sense? Okay. So we are going to be talking about exponential decay and modeling it using tables, graphs, and equations. All right. So please open your book to investigation 4.1. Oh, you've already gotten there. You are very smart, Jenny. And you laugh. Nice. Okay. So, I've stopped the Forrest Gump thing. No, okay, that's different. All right. So the exponential functions you have studied so far have all involved quantities that increase. This investigation you will explore quantities that decrease or decay exponentially as time passes. Making smaller ballots. Introducing exponential decay. In problem 1.1, you read about the ballots Shen is making. Shen cuts a sheet of paper in half. He stacks the two pieces and cuts them in half. And then Shen stacks the resulting four pieces and then cuts them half again, and so on and so forth. Because who doesn't love cutting ballots out of one piece of paper? All right, so Chen has a very special piece of paper that has an area of 64 square inches. That's not normally how paper is, but that's cool that Shen has this special paper. And so he cuts it in half, and now he is left with 32 square inches per ballot. After two cuts, each ballot has 16 square inches. He is going to continue to cut the ballots 10 times, and so that he has a whole bunch of ballots, but they're going to be really, 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 really small. And we want to figure out the area of each ballot using the pattern that we are seeing or observing in this table. In question B, how does the area of the ballot change with each cut? Write an equation for the area of a ballot after any cut n. Yes, you're going to make a graph of the data. And then for E, I know, hold your excitement. Please, Mikey. How is the pattern of change in the area different from the exponential growth you've studied? How is it similar? There are similarities. It's not going to look very similar, but there are similarities. I really want you to search for them. How is the pattern of change in the area different from linear patterns you have studied? How is it similar? Okay. Are there any questions about what you're being asked to work on with your partner for the next 20 minutes or so? It should not take that long. 20 minutes should do the trick. Okay. Please answer questions A through E. And remember, we are looking for how to model exponential decay in tables, graphs, and equations today. Go get started.